All right, so because we had difficulties in putting forward the lecture notes on Friday, I'm going to cover them briefly here on this YouTube video. This is Lesson 8, and it's dealing with the idea of reversible and irreversible processes and what makes up that term irreversible, what defines it versus a reversible process. As I mentioned in class on Friday, there is a really powerful aspect of state functions in that they are path independent. And so because they're path independent, we can look at hypothetical paths in a change from state 1 to state 2. So you'll notice that right here we've got state 1 occurring at a certain temperature 1, volume 1, and state 2 occurring at temperature 2, volume 2, and then there's an actual path happening between them that describes the change in internal energy, the specific internal energy. There's a lowercase u here, but there is this delta U actual that we're seeing, which is the change in internal energy. So if I want to go from state 1 to state 2, I have that nice smoothwise curve. The interesting thing is that I don't actually need to use that path to calculate what would be the change in internal energy of the system. So I could take hypothetical paths from step 1A down through step 2A. I could go up through step 1B to step 2B, down to step 3B, and down to step 2A. I can choose any of these paths, and at the end of those additive paths, I will have the energy difference, the delta U, for state 1 to state 2. So, a change in state functions, again, is path independent. That's why we say it's path independent, is because I can choose an isothermal and isochoric process and get from state 1 to state 2. So in this particular plot, we've got a TV space plot. And you want to look at that figure from the textbook and say, what is TV space? It's temperature and molar volume space. So in general, these plots are going to have two axes, and they're going to be a part of what we will call phase space. But changes in parameters get specified. So temperature volume space, pressure volume space plots are going to pop up all over this class. Okay? And yeah, and the idea here is that we're talking about the space described by variables. This is an abstract space, so temperature volume space, pressure volume space comes up quite a bit. Now, given that a change from state 1 to state 2 is called a process, that's language, it's basic language in this class. Most of the key processes that we're familiar with have a direction in time, right? They go in a certain direction. We know that they're supposed to go in a certain direction. Although we're not stating that in this chapter 2 work where we're only dealing with the first law. The first law actually doesn't tell us which direction a process is going to go. We find that out through the second law, and because of the second law, an implication of the second law is something called the arrow of time. So you've seen here, we're going to jump ahead to figure 3 in the textbook. Just to give you a little preview, we've got 3 different key processes that are called irreversible, okay, irreversible processes. And the thing about them is they have directionality. So if I were to open a valve in a pressurized gas tank, as you see in that first one, the gas spontaneously leaves the tank. That is a spontaneous process. You don't see the gas suddenly jumping back into the tank. No, we'd have to pump that back in for that to happen. The spontaneous process is pressurized gas leaving the tank. Reversible processes, in contrast, are interesting, not because of that word reversibility, but because if I have a reversible process, a truly reversible process, it's actually impossible for me to tell which direction that process is going because reversibility doesn't happen without energetic compensation. So in this case, as I was saying with the gas tank, you'd need to pump energy back in to cause a reversibility of a spontaneous process. So this is a slight correction here in what I was talking about. If I want to reverse a spontaneous process, I need to pump energy and mass back into the system. A reversible process, quote-unquote reversible, is one where we can't tell the direction. And energetically, it would go either direction just as easily. In a spontaneous process, there's really only one direction that the process will go, such as a hot block cooling down. So if this is my little hot thermal block, over time I'm going to radiate out heat or conduct out heat, and I will end up with a cooler block of metal, wood, you name it. But that block won't spontaneously heat up. In fact, I'd have to pump energy into the block in order for it to heat up. And the third example that you see down here are two gases that have a barrier between them, a membrane. And when that membrane is removed, well, then you have a mixing of gases, and you can't unmix the gases at the end of an irreversible process. So, again, what is a quote-unquote reversible process? It's, again, I mentioned this on Friday, it's more than just thinking about something that goes one direction versus another direction. It's actually, in thermodynamics, that word reversible is for an idealized or a best case process. And again, you cannot, in a reversible process, you cannot implicitly tell the path or the direction. So, if I were to start using the examples in the textbook, I would start with irreversible processes and use hypothetical paths to describe them. So you're going to see in Figure 2.4 from Chapter 2 of Koretsky an example where I have a 1,020 kilogram mass on top of my piston that is forming an external force over an area. Force over an area would be a pressure. And there's going to be a process A whereby that mass is removed. And when the mass is removed, the internal energy, the internal pressure pushes that piston up. And you see a change in this where I have first a change in volume followed by a change in pressure. Okay, I'm actually going from state 1 to state 2, and I am using two hypothetical paths, a change in molar volume first, that would be an isochoric change, followed by a change in pressure, an isobaric step next. And then I have a block underneath here that would be the energy that is work, expressed as work going out of the system to the surroundings. And this plot itself is a PV space plot where I'm plotting external pressure. So I have isochoric and isobaric hypothetical steps, and what you notice is that I have a certain amount of work given by the same area under the curve. Now if I put that mass back onto the piston and I have an isothermal compression, notice that these two were both isothermal processes, so the temperature part isn't plotted here. But in adding the weights, I'm going to do the reverse of that path, where I'm going to have an isochoric expansion and isobaric change of volume, right? And I would have more work being given by the area under this curve. So that's work going back in to the system when that weight is added. So let's compare this where I start dividing up the where I start doing this as a calculation. So if you look at equation 2.8, I'm going to have specific work for path A. The path A is process A, and you see that I have my integral for pressure and volume change, and at atmospheric conditions that's going to give me a total change of 4,000 joules per mole. And we notice that it's a negative sign because work was being done outward to surroundings. The energy was leaving the system as the mass was removed from the piston, and I had an isothermal expansion. You can go ahead and pause this for a second if you'd like. And now I'm going to keep going and say, okay, work is leaving the system. So if I look over at work of path B, the isothermal compression, I notice that my path direction changes, and I have a, oops, let's go back a few. The direction changes, and I go from V1, instead of going from V1 to V2, I go from V2 to V1 in my integral, and I have a net positive change of energy, 8,000 joules per mole, pumped into the system. Positive energy going into the system is positive. If I sum those guys together, I have the net work from an expansion and a compression cycle of processes, which is a positive 4,000 joules per mole to lift a weight off and put the weight back onto the system. So feel free to work that example again, noting the difference in the volume and noting that we have, again, to follow the negative sign convention for pressure because we're reflecting the external pressure. In this case, the external pressure is atmospheric pressure. That process, those two processes are going to be, well, the first process is irreversible, right? We have an irreversible expansion. And I put the weight back on, and I put energy back into the system. Two irreversible processes. One is spontaneous, the other is compensated by the mass added into the system. What you end up with over on the lower right is an amount of energy dissipated or lost, energy that's lost to the system. So 4,000 joules per mole are lost to the system, and 4,000 is given to the by the area under the curve. This will start making more sense when we look at the following example. And all I'm really doing here is I'm working the examples described in your textbook by hand, which is the recommendation that I have for all of you to do to gain better insight into what is reversible versus irreversible in processes, which is going to be fundamental to your understanding of the class. So if we break up that mass into two chunks now, I have 510 kilogram masses, two masses, and I take them off in two steps, and I add them back on in two steps. So I have process C, which was two steps of isothermal expansion. Again, noting that this is isothermal. There is no temperature change going on in this gas. It's just energy change. And then we have isothermal compression when I put those blocks back on. The interesting thing here is, yeah, I can run this path for process C. The work for process C is going to be negative V1 to V2 of the external pressure, 1 atmosphere, right, or the atmospheric pressure. And we've got the mass change times the gravitational constant over area to give me my additional adaptation. And ultimately, you see that I have negative 4,667 joules per mole. That's a larger number than I had before. So when I had two steps of masses, I got more work out of the system. Flip that back around to have a compression, and what you're noticing in red that I am integrating different values here, and I'm going to have 6,667 joules per mole that is put back into the system, giving me a network of 2,000 joules per mole. I want you to go back, take a moment, pause, compare to earlier. Was this more work or less work that was input into the system? That's a positive, so work is being input into the system. Another way to look at this is to say how much area was lost to the surroundings, and that's that upper box. And you can see a smaller area that's been lost to the surroundings, and so less work is required to arrive at the same change in state. I go from state 1 to state 2. There was no difference in state change. Energetically, I end up the same. The amount of work is different. And so we get to that end member that I was describing at the very middle of class on Friday. Let's say I have an infinitesimally small mass, right? This is a partial change in mass relative to all other variables in the system. And I take those out bit by bit, and I have an isothermal expansion that is smoothwise removal of mass. And then I put that mass back on to an isothermal compression, but I've just divided this up into like effectively atoms of mass exchange. And in doing so, I note that that mass is divided into differential units, and I can do the path for that work. I can calculate that path, and you see that my path now has a natural log function in it because I've ultimately started integrating 1 over the value of interest. 1 over v, the integral solution for that would be the natural log of that difference. Keep that in mind. That's going to be very important in time to come. So I have a certain amount of work out. You notice that that number keeps on changing. The work for the compression step, similar form, sign is different. And the sign is different because V1 over V2 versus V2 over V1 is different. That's a directionality aspect. And those two values are the same, but instead of being different values, they're the same value that just have a sign change, which means that my net energy is 0. My net work for those two cycles, for those two processes in a cycle, is 0. That is a reversible process, where I have no area above the curve, I have no energy dissipation, I have the best energy output possible. The best case scenario is what reversible means. So if I were to think about reversibility as the best case scenario instead of which direction something's going, it's an example of best case scenarios, then I can actually frame that in terms of an efficiency equation. So if I had an expansion process, efficiency would be given the Greek letter eta, eta, eta. So it looks like a curvy N, but it's the Greek letter eta. And I'm going to have the expansion process where I have the irreversible work divided by the reversible ideal. And the compression process is the same general form, but we would be inputting the work to cause the compression process relative to the reversible work. Again, we've got the real case with energy dissipation in the numerator and the best case, the ideal case, in the denominator. So we should never get a value greater than 1. Think about that. That the energy in the numerator for the work should always be lower than the energy in the denominator for the ideal process. Otherwise, once we've reached 1, we've received an efficiency for a process that is the ideal. Yes, a good check is to see that this is a unitless fraction that we're describing. This is just a decimal value from 0 to 1. It's not a fraction until we would multiply it by, say, 100%, where the percentage sign brings in the identity for out of 100 units. So yes, this is unitless fraction 0 to 1 in decimal form that you would be reporting. You would not be reporting percentages unless you made the conversion to 100%. Our engineering strategy for this is oftentimes going to be to solve for an idealized, reversible process and then correct for that idealized process using an assigned efficiency factor. So we would calculate what is the best case reversible process, and then we'd multiply it by that efficiency factor somewhere between 0 to 1 to solve our problems. And that's going to come up in the future. You don't need to know that right now. Coming up in the lecture next time is going to be discussions on enthalpy and heat capacity. I would welcome you to go back in this particular lecture short, take some notes by yourself, make sure you work through those examples that I just worked through also. There's a lot of learning in here about what is the difference between an irreversible process and a reversible process. The reversible process, again, is like that best case scenario for what could happen, thermodynamically speaking. All right, until next lecture, guys.